So in this lecture, we continue with studying saturation, and we look at a slightly more complicated example. And again, we will not be able to explain all the computations in it. Then we will study a little bit about how saturations are done, and then we can revisit this problem. Okay. So let's look at the example. So this is taken from this book of Cox-Little-NOC, chapter 4, section 6. Okay. So the ideal is generated by xz minus y squared, yx cube minus yz in a polynomial ring in 3 variables. Okay. And so we just use some field, finite field of 100. This is a prime number. So I is ideal by this. So just by looking at this, we notice that every term of every generator of I involves x or y. So I is contained inside the ideal generated by xy. In other words, z of I. So when we say z of I, it's not over this field, but it's over the algebraic closure of the field where it was defined. It was defined over some field, but when we talk about z of I, we mean the algebraic closure of that. Okay. But anyway, that's not in the calculations. It's just a remark. So z of I will contain, I is contained inside here. So z of I will contains the I is inside here. So z of I contains this. But what is this? What is the point where x and y would vanish? It is a z-axis. Okay, so we will try to saturate this ideal one variable at a time. That's what we learned. If you need to remove the component corresponding to x comma y, then we need to saturate this ideal here. We'll see if this is okay. So we'll do it for one generator at a time. Okay, so let's saturate x, and then I2 is saturate y. Okay, so then we just notice that I1 and I2 are the same. Okay, and so this and this is the given generator, and we have a new generator x squared y minus z squared, which is not in the ideal given by x and y. But since these two saturations are the same, so it's equal to I colon the saturation of x comma y also. Okay. So in the next lecture or later in this lecture, we will study some approach just to computing saturation. Right now, we will just continue with this thing. So we need to understand this prime ideal, this ideal now. What does it look like? Okay. So the observation that we make is this is the kernel of a ring map from R, which is k x y z, to kt. X goes to t cube, y goes to t to the 4, and z goes to t to the 5. And the exercises, I will give a hint on how to prove this. Okay. So in other words, this given ideal I1 or I2, which are same, is actually a prime ideal. Okay. So what have we concluded so far? We have concluded that here is a prime ideal, and any other prime. So this, as soon as you saturate x, we get this prime ideal, or as soon as you saturate y, we get this prime ideal, which means any other prime ideal, any other minimal prime, which is not this I1 equal to I2, must contain x and y. But notice that x comma y itself is a prime ideal containing this ideal. So there are only two minimal primes, I1 and x comma y. Okay. So now so for the component corresponding to I1, it itself is the primary component. Associated prime and the primary component ideal are the same, because okay. But for the other one, let's take an element inside here. So notice that x square y minus z square is not there in this ideal. So if you saturate I with respect to this element, we would pick out the component corresponding to x comma y, and it just says x comma y. So therefore, we now have concluded that I is I1 intersect this, I1 intersect x comma y, and we ask, I take it back. We have concluded that for the minimal component, the minimal components are I1 intersect x comma y, but there could be an embedded prime which we don't know. So we ask, okay, so we intersect I1 and the ideal generated by x and y, and we ask intersect that, and then we ask is I equal to that, and it says it is true, so which means we have now found the primary decomposition, which is I equals I1 intersect x comma y. Okay, so this example we will discuss after we study some techniques behind computing saturation. So this is about computing saturation. So recall that if R is Noetherian, when we say computing, it mostly refers to some polynomial ring or a quotient of polynomial ring, but we will develop these ideas in slightly generality. R Noetherian, I and J ideals, then I colon J the J saturation of I is I colon J M for all sufficiently large M. Okay, this is what we know. Okay, so if you want to find saturation, it's sort of enough to understand how to compute colons. Hence, okay, so in principle, we could just compute some I colon j square, I colon j cube, and at some point try to guess whether it has stabilized, and then use that as and decide whether that is a saturation. Okay, so that's the so we could do that. So if you can just learn, okay, so to compute I colon j saturation, okay, we need to know just I colon j, different j, as j runs over various things. Okay. So we need to know to compute I colon j. Okay. Some colon of two ideals. Okay. But how do we, what about these? So if say J is generated by G1 through Gm, or some Gn, let's say, okay, then I colon J is intersection of I colon Gi. Okay. So algorithmically, if we know how to intersect and how to take colons with one element, then we can do this. Okay. So therefore, we need to learn two things: how to intersect ideals and how to take colons. Okay. So without loss of generality, for now, as far as colon is concerned, we can assume that J is principal. So proposition. Let R be a Noetherian domain. I R ideal, okay, and G inside R. Okay. Write I intersect the ideal generated by G as, so every generator of this is going to be divisible by G, as H1 will be a multiple of G, so that's what H1, H2G up to some HM times G. Okay. Then I colon G is equal to H1 through HM. Okay. So just let me read this once more. So we have an ideal and an element G, and we want to know what I colon G is. So to compute I colon G, we first express I intersect G. So I intersect G would be finitely generated, and every generating set will be a multiple of G. Every element in a generating set would be a multiple of G because it's a subset of G, and then the colon is just this H1 through HM. Okay. So we are not saying that H1 through HM is unique or anything. Just take any generating set, it will have this sort of a form, and then just remove the G from them. Okay, so that's a proposition. And just one more observation. This is not, we'll have to prove it, but notice that if you take I colon G and then multiply them by elements of G, it actually lands inside this intersection. Okay. It is inside I by definition, and it is also inside G because there are multiples of G. Okay. So it does land inside that intersection. Okay, proof. Okay. So H1 multiplies G into I. Therefore, H1 is in I colon G. Okay. HIG is inside I. So I contains, I colon G contains H1 through HM. So this proves one inclusion. Okay. And this inclusion does not, we didn't use the fact that it's a domain. It's just, okay. So now let's do the converse. So let A be an element of I colon G. This implies that AG is inside I and is inside G. Okay. Therefore, we can write it as AG as some coefficients Ri times HI times G. I goes from 1 through M. Which, okay, so now we can, therefore, we can write G times A minus Ri HI is equal to 0. Now, R is a domain, so A must be equal to, so A is in the ideal generated by the HI. It's a combination of the HI, H1 through HM. Which is what we wanted to prove. I colon G is in the right side. Okay, so this is where domain is used. Okay, so this gives us a way to compute I colon G, that this proposition. Okay. But okay, so let's go back where we were. We wanted to be able to take colons of, well, we wanted to do saturation. We wanted to do saturation. That we concluded that if you can intersect, if one can compute colon ideals arbitrarily, then one can do saturation also. For colon ideals, we have to do, for taking colon ideals, we need algorithms to do two things. One, intersect ideals and then take colons of ideals of principal ideals. So the principal ideal part is what we just described. But that itself involves taking an intersection. Okay, so it might be useful to learn to do the intersection first. So let's do that now. Okay, so this is, okay, so let K be a field. So this is, now we will restrict ourselves to our computational setup where we can actually do these things. Let K be a field. R is a polynomial ring in n variables. Okay. I is an ideal generated by F1 through Fm, and J is an ideal generated by G1 through Gn. Okay. So both are ideals. Okay. Let S be a polynomial ring in one extra variable, x1 through xn. Then I intersect j is the ideal generated by t times I inside S plus 1 minus t times j, both are inside S. So this is an S ideal contracted to R. Okay. So let's just read this. So this settles the question. This gives us a way to compute an intersection of two ideals in a polynomial ring, okay, which can be used now to address this part of intersecting I with a principal ideal, okay, and then somehow we have to divide this. So that's okay. And then it also takes care of this intersection of these colon ideals. Okay, so essentially, if we understand this, if you can use this theorem, then we will be able to do saturation by hand with the help of a computer. Okay, of course, you can ask it to saturate, but that's not what we meant. Okay, so we'll prove this theorem and then go back to that example. So first of all, I hope this is clear what is meant here. So this is the ideal generated, maybe I should just write. This is the ideal generated by t times f1 up to t times fm, that's t times I, and this is the ideal generated by 1 minus t g1 through 1 minus t gn. Okay, so it's okay. So it is an S ideal, and that contracted to R would be I intersects J. So proof. So notice that, so we would like to consider an F inside, let F be inside I intersect J. Okay. Now, so what does it mean to say that F is inside I? So this now implies that TF is inside TI and 1 minus TF is inside 1 minus Tj, because F is in both I and J. So now this implies that F, which is a sum of these two things, is inside Ti plus 1 minus Tj. Okay. So therefore, I intersect J is inside Ti plus 1 minus Tj, and it is inside R. Okay, so this is one, F is an element of R, so it is inside, okay, so we get this. So now the other direction. So let F be inside Ti plus 1 minus T times J. Okay. Okay. So now we can write, because it is inside here, we can write F as some, so F is a polynomial of just X, as some G, polynomial G of X comma T plus some polynomial H X comma T, okay, where this belongs to T times I and this belongs to 1 minus T times J. We are just saying that F is in the sum of these two ideals, so take one part from here and one part from there. Okay. So now let's look at what happens when we put 0 for this. Okay. So put T equals 0. Nothing happens to X because T does not appear in it at all. Okay. We get G of X 0 plus H of X 0. But what are these? Well, this is, so G is in Ti, so it is going to be T times some element of I, but some element t times some S linear combination of generators of I, okay? Not an element of I, but an element of the extended ideal. So S linear combinations of elements of I times t. So when you put t equals 0, we just get this to be 0. Okay, and here we would just get some h of x, which is, one can check without much difficulty that this is actually inside J. So when you substitute 0 here, so notice that, okay, so we can write h of x 0, so we can write h of xt as 1 minus t times some element inside the extended ideal of J to S. So it is linear combination of the g's with coefficients coming from S. When you substitute t equals 0, this just becomes 1, so we can take that out. Then the generators are untouched, and the coefficients we put t equals 0, which means we just get the degree 0 part in t, which is just some elements of R. So this is in J. Okay. Similarly, put t equals 1 to get, so this says that f of x is inside J. That's what we just concluded. To get f of x is equal to g of x 0, this is inside I, plus h of x 0, which is 0. So therefore f of x is inside I intersect J. So this is the proof of this theorem. Okay, so let's just okay. So now we have an algorithmic plan, which is what? So if you want to intersect two ideals, so with notation as in the theorem. Okay, give monomial order, give Lex order with t bigger than x1 bigger than x2 up to xn, then compute a Grobner basis for ti plus 1 minus t j inside S. Okay, and so this would now imply, so from this now take from this Grobner basis, okay, select elements that do not involve T, and this gives Grobner basis for I intersect J. Okay. And then we can repeatedly, we can do it for principal ideals, their intersections, etc., to now get semicolon and intersections. Okay. So let's just do this, not the full thing, but in part in the previous example. Okay, so this is again the same example, the continued example that we saw in the last lecture, which is R is ZZ adjoint mod 101. So just any field, not very big, so that the computations are faster. X, Y, Z, ideal is xz minus y square and x cube minus yz. Okay, and we would now like to saturate x and saturate y, and we will like. Okay, so let's see how what we just described now. We will let's try to do that. Let's illustrate that. So now we construct this larger ring T x, y, z. Monomial order gets Lex because we wanted to use it for elimination, and then we just take T times. So we need to use a sub command. This is the, if you have same set of symbols, variables, like x, y, z are both in R and in S. So then we can, if you just write sub I comma s, it would just extend the ideal and now treat x, y, z as elements of S. Okay, so please look it up in, this is sub is for substitute. So please look this up in its help in my column. And so t times, so this is just the extended ideal, t times the extended ideal of I times 1 minus t times x. Okay, so the x here refers to x of S, which is why we didn't have to put a sub there. Okay, so we get some ideal here. Okay, and then we need to eliminate t from this ideal. So we asked for to eliminate, and I didn't print it. So what is this? Eliminate j comma t slash f slash some function here. So this is an abbreviation for the apply function. This is the same thing as up. So eliminate j comma t will give some list, and now to that list apply this function. Okay. That's so it gave some generators. Now okay, so this is just a programming issue. In all these in this context, the variables x, y, z refer to those in S, not in R. But here we would like to construct an ideal in R, removing in any case t is not there. So so what are we doing here? Take this list. Okay, so yeah, so eliminate j comma t applied to this function would just say would just rewrite the function. So eliminate j comma t is this list, but them thought of as elements of S. So we're just using a sub again to convert it to elements of R. Okay. Use R just to say now the variables refer to those of R, and then we ask it to divide these elements by, so this is so OOO refers to not the previous output, the output before it, which means to the output of this list here. So to each element in that list, each element I in that list, divide I by x. But when we do this, it goes into what is called the fraction field of R. So given a domain, integral domain, one can localize at the at the complement of the 0 prime ideal and get a field, which is, these will be exercises. And then so you will get an element in the fraction field of R, but of course these were divisible by R by x, so that we know. So therefore we just convert it back to R. Okay, so for example, when we apply that, run that command to this, we would remove x from here and x from there. So minus y square plus xz, here x square y minus z square, and this is what the saturation was for x. Notice that when we saturated, this is what we had got. Okay, y square minus xz, z square minus x square y, and x cube minus this. And notice that, that's exactly what we got here. Okay, so this is the end of this lecture, and in the next lecture we will start discussing a new topic, which is about. So first would be sort of an introductory lecture on what these morphisms between rings mean for spec. And then we will use that as a motivation to study what is called finite morphisms or integral morphisms. And in that course of discussing that, we will prove a theorem called Hilbert's Noether normalization lemma, and from which we will derive a version of Nullstellensatz, from which we will prove the Nullstellensatz that we had used earlier.